Hi, this is part 2 of chapter 2, conversion and reactor sizing. So in part 1, you have learned on how to define the conversion, and also second, you have learned how to develop design equation for batch and flow reactor. So for part 2, so in this video, we will look into applying design equation to calculate reactor volume for a particular process, and also to evaluate best reactor arrangement for a single reactor. So you will focus on single reactor. Okay, let's first just recap back all design equations that we have developed in the previous lecture on part 1. Okay, these are the summary of all the design equations, so you should at least be able to memorize the differential form of the equation. So for batch is one, for CSTR is the algebraic form, for PFR is this one, and last one for PBR is this one. Okay, so first we look at into the reactor sizing for flow reactor. So when talking about reactor volume, we only refer to flow reactor. Okay, for batch reactor, the design equation is used to determine the reaction time required for a particular process. Remember in our experiment last week, we have compared between two different sizes of batch reactor, and it shows that the size of reactor doesn't have any effect to the conversion of the reactant in a batch. In this lecture, you will learn about using Levenspiel plot. Okay, using Levenspiel plot to estimate reactor volume. Okay, in engineering problem, you will be given a set of data for reaction rate and also the conversion X. And also we given you the known FA0, the initial molar flow rate. So you will use the data to plot the graph of FA0 versus X. Okay, remember the design equation? This is for CSTR, and this is for PFR. So why do you have to plot the graph of FA0 over minus RA versus X? Okay, if you look at the CSTR equation, V equals to FA0 over minus RA times X. And for PFR, the volume will be V equals to, you have FA0 over minus RA on the y-axis, and you integrate from 0 to x to the dx conversion. Okay, first we focus on the reactor sizing for a CSTR. Okay, so for CSTR, for a single reactor, for a single CSTR, we always refer to the final conversion, DXF, final conversion. Okay, so look at the design equation for CSTR. We have V equals to FA0 over minus RA times X. So FA0 will be on y-axis, and X, the conversion, will be on x-axis. Okay, so let's say you have this plot. Okay, you have FA0 over minus RA on y, and you have X on the x-axis. So your plot is something like this. Okay, so the question gives you that the final conversion is 0.8 or 80%. So from x-axis, remember CSTR is always referred to the final conversion only. So you go to the x-axis. From 0.8, you go up until you touch the plot, and then from there you go to the left and touching the y-axis. So the volume of CSTR will be this amount, this value on y-axis times the value at x-axis 0.8. So this area will be the volume of CSTR. This is V CSTR. Okay, let's say you have different plot. Okay, so we move here, and this one we move here. Okay, let's say your plot is something like this. This is your x, and this is same FA naught over minus RA, and your plot is something like this maybe. So what is the conversion? Let's say it's the same thing, 0.8. So what is the volume? Okay, so the volume of the reactor still from 0.8, you go up touching the line, the plot, and then from the cross section of the plot, you go to the touching the y-axis. So this will be your volume of CSTR. CSTR. Oh, if let's say you have another plot of this one, x and FA naught over minus RA, say your plot is something like this, and your final conversion is 0.8 here. Okay, so the volume of your CSTR will be from 0.8 go up, touching the plot, and then go here. Okay, so your volume will be of CSTR will be this one. Remember, always the final conversion. Okay, another example. If let's say your plot will be something like this. So your x FA naught over minus RA, and your conversion is here 0.7, let's say. So your CSTR volume still touching the plot from 0.7, touching the plot and hit to the y-axis. So this will be your volume of CSTR. So it means that for CSTR volume, it must always a rectangular or square. Okay, so finish on the CSTR. Now we move into the PFR. Okay, so from the data is given to you also the minus RA and the conversion, and also given to you the node FA naught. Okay, so you will plot a graph, a 11 speed plot of FA naught minus RA over minus RA versus X. Okay, let's say the plot is something like this. Okay, and the conversion given to you is here. Say so 0.8. So the area, the volume for PFR will be always be from 0.8 touching the plot here. So the volume for PFR will always be under the graph. So this is VPFR. Okay, let's say you have different example, different plot. Okay, let's say something like this one. Okay, you have SUS X and FA naught over minus RA. Let's say you have a graph of the level space plot looks like this. So your volume of PFR will be from 0.8 touching the plot, and this all the area under the curve, under the graph, will be the VPFR. Okay, say you have another plot of here, and you have something like this. Okay, with this is the X 0.8. Okay, so your PFR volume will be from here, all the area under the curve, VPFR. Okay, so in the conclusion, the area of PFR will VPFR, the volume for PFR will always be under the curve. Okay, always area under the curve. Okay, let's look at example 2.2 and 2.3, sizing a CSTR and PFR. Okay, so the question given to you is the reaction of A producing B is carried out in a CSTR, and the entering molar flow rate given to you, FA naught, equals to 0.4 mole per second. So using the data in table 2.1, this table, calculate the required volume, the volume required to achieve 80% conversion. X equals to 80%, which is equals to 0.8, and shade the area of level space plot that corresponds to this conversion. Okay, so the first thing, what is the first thing that you have to do? Okay, so first thing, given to you the FA naught, you need to calculate FA naught over minus RA at each conversion. Okay, so you will have FA naught over minus RA for x equals to 0, 0.1, 0.2, 0.46, 7, and 8. Then once you have the data, okay, so you will have the data in this table. So you have FA naught over minus RA here. So using the data, you draw a level space plot, and please use a graph papers. Okay, say you have from the data, you draw a level space plot. Have this one, so label the axis. Y is FA naught over minus RA. So let's say your data, your plot will looks like this. Okay, so then look for the required conversion. So for this question, it's given to you that the conversion will be 0.8. So from x-axis at 0.8, you draw a straight line vertically. It go vertically, touching the plot of the graph, and then you draw a horizontal line crossing the y-axis. That will be the value of your y-axis. This is the value of y-axis, and this is the given conversion. So the volume V CSTR CSTR. Okay, you have at 0.8 your at 0.8 your FA naught over minus RA is 8. So your VCSTR will be 8 times 0.8, which is equals to 6.4. Look at the unit, meter cube. Okay, so let's say if, for example, the question said the final conversion is x equals to 0.6. So you look at the point at 0.6. Say 0.6 here. So look at the point from here, from 0.6, go to the y-axis. So the VCSTR for conversion at 0.6 will be, look at the table, FA naught over minus RA is 3.54 times 0.6. Then you will get the volume in meter cube. Alright. Okay, so for PFR, remember that the reactor volume will always be the area under the graph. So the first thing you need to do is write down the design equation. So it's given to you here, the design equation. This is for PFR. So you need to integrate the area from x equals to 0 until x equals to 0.8. Okay, the first thing that you need to decide is how many points that you have. Okay, remember that the interval between 2 points, between point x to x1 to x2 to x3, it must always be the same. Okay, so look at your x value. Okay, you have your x value here, you have 0, 0.1, 0.2, 0.4, 0.6, 0.7 and 0.8. So you have odd and even number of the conversion. So from here you can actually remove the 0.1 and also 0.7. Okay, now look at this one. This will be your x0, this will be your x1, 0.4 is your x2, 0.6 is, so it's your x3, and 0.4, 0.8 is your x4. So look at, you have now you have same interval, 0.0 to 0.1 you have 0.2 interval. So from 0.1 to 0.2 you have also 0.2 interval. From 0.2 x2 to x3 you have 0.2 interval, and also from 0.3 to 0.4 you have 0.2 interval. So it is important that you have the same interval for PFR, for the integration. Okay, now, so how many points you have now? You have the x 0.1, 2 points, 3 points, 4 points, 5 points. Okay, so since you have 5 points, so you can use 5-point quadrature formula. Don't worry, this equation will be provided to you during the test and also final exam. This will be given to you, but you need to know which equation to be used. I also provided the attachment together with your lecture notes, so you can refer to the equation in the appendix as well. Okay, so now let's calculate the volume of PFR for this question. Okay, so you have the equation. So V PFR will be equals to H over 3. So calculate aside, H will be equals to X4 is 0.8 divide by 0, X0 equals divide by 0.8 minus 0 divide by 4, which is equals to 0.2. So 0.2 divide by 3 times, so you have F naught is 0.89 plus have 4 times F1 is 1.33 plus you have 2, F2 is 2.05 plus you have 4 times 3.54 plus last one is 8. Okay, so your VPFR will be equals to, use your calculator, you will get 2.165 meter cube. Okay, so compare with your CSTR volume. Okay, remember your calculated VCSTR equals to 6.4 meter cube and your VPFR equals to 2.165 meter cube. So for same process, your PFR required less volume compared to your CSTR. That's because your plot is something like this. So because you have this plot, your level space plot looks like this, and remember your conversion is 0.8. So for CSTR, the volume will be this one, the square, and for PFR, your volume is the area under the graph. So for this process, the preferable reactor will be, okay, so PFR. So for this particular process, PFR is preferred. Okay, it is preferred because small reactor can save cost, which is desirable, and at the same time it's also save space, but it still can achieve the same conversion of X equals to 80%. Okay, so I hope by now you are able to calculate the volume of CSTR and also PFR using Levenspiel plot for a single reactor. Okay, so before I end this lecture, this is some important things that you have learned and you must remember. So you need to know the general mole balance, and then you need to know how to develop the mole balance equation for each reactor. Remember, we have 4 types of reactor, and then you also need to know the design equation for each reactor. You also have 4 types, and then you learn about the conversion what is the conversion and how do you relate with the mole balance. And lastly, you have done the reactor sizing for CSTR and PFR for a single reactor. Okay, so up to this point, we have done all the 4 outcomes for chapter 2, which is to define the conversion and learn how to develop design equation for batch and flow reactor, and also you apply the design equation to calculate the volume of reactors for a particular process, and then you compare, evaluate the best reactor arrangement to choose which one is the best reactor for that particular process. But this is done only for a single reactor. Okay, so in the next chapter, in the next lecture video, I will explain on reactor sizing for more than one reactors. So you have more than one reactors. Okay, thank you for watching, and I hope you are able to understand. If you have any problem, please discuss with your group mates. And later we continue with part 3 of chapter 2. Thank you.